This video takes a look at our final Chapter 19 worksheet, which is dealing with functional groups. So organic compounds can be grouped into different classes or families based on what we call a functional group. Functional groups are an atom or a group of atoms other than carbon-carbon bonds or carbon-hydrogen bonds that are responsible for chemical behavior. This table here is slightly different from the one in your book, but it's containing the same materials. So some common families we have are alkanes. Alkanes don't have a functional group. They just have the carbon-carbon single bonds and carbon-hydrogen single bonds. Alkenes are going to have a double bond between carbons. Alkynes will have a triple bond. Arenes, so those we said were aromatic compounds. They're going to be categorized by having this chain, it's a ring structure, of carbons with alternating double bonds. So we're going to see this, what we call a benzene ring present. So it is this ring structure with the alternating double bonds that classifies something as an arene. Alcohols are going to have an OH group. And so notice endings. Alkene has an ENE ending, alkyne, YNE. Alcohols have an OL ending. Ethers are going to have an oxygen in the middle of carbons. Amines are going to contain a nitrogen. Aldehydes, and we're going to go into each of these in some more detail. Aldehydes are going to have the C double bond OH. Ketones are going to have a C double bond O in between carbon groups. Carboxylic acids are going to contain what's called a carboxyl group. It's a C double bond O attached to an OH. Esters will have a C double bond O, but they're in between carbon groups. And then an amide will have a nitrogen next to a C double bond O. You need to have your functional groups memorized. You need to recognize the atom grouping and the corresponding family name. So one of the things we need to be able to do in this chapter is identify functional groups in the following molecules. And it takes practice. So we can look first of all at acetaminophen. And the first thing that stands out to me is this ring structure. So that ring structure is going to classify this as being aromatic. And for our functional groups, we are looking for anything other than our basic carbon-carbon single bonds or carbon-hydrogen single bonds. So I see some other elements here. I see this OH. Now I have a couple of functional groups that have that OH present. So I've got to look to see what the OH is attached to. If it's just attached to a regular old carbon, then I have an alcohol. I also see that I have a nitrogen, and I have a couple of families that contain nitrogen. In particular, I've got two. I have amines and amides. So amines will have the nitrogen attached to just a regular carbon. The amides will have it attached to a C double bond O. So we always need to look to see what it's attached to. So my nitrogen here, on the right side, it's attached to a C double bond O. That makes it an amide. So acetaminophen, commonly known as Tylenol, has this particular chemical structure. It consists of an alcohol group, it has an aromatic group, it has an amide group. So it's classified into 3 different families. Each of those groupings gives it particular properties. Now next, if we look at aspirin, again, something that stands out to me right away is that 6-carbon ring with the alternating double bonds. So that is going to make it aromatic. I also see some oxygen. So I see this OH. Again, we look to see what OH is attached to. Here, it's attached to a C double bond O. When OH is attached to a C double bond O, that is a carboxylic acid. And then I see another C double bond O. We always look to see what they're attached to because I have several families with a C double bond O. That C double bond O is attached to an O, not an OH, but an O. So this is an ester. Now if we look at our next set of compounds, I have estradiol and testosterone, so two common hormones. If I look at the estradiol, again, I see the 6-carbon ring. I have other rings, but there's no alternating double bonds. Those are not functional groups. Those are just carbon-carbon bonds. But the alternating double bonds makes it aromatic. I have an OH. I have an OH. So it is also an alcohol. With testosterone, I also see the OH. So it's an alcohol. Again, all of these rings that we see, there's not the alternating double bonds. So those are not aromatics. Those are just regular old carbon-carbon bonds. I do have this double bond here. It's just a double bond between carbons, so that makes it an alkene. And then I have this C double bond O. That C double bond O is attached to other carbons, so it is a ketone. And again, we're going to look at each of these functional groups in more detail. Now, looking at I told you the functional groups were going to govern properties. So if we look at aspirin and acetaminophen, they are both common analgesics, both common painkillers. And so we're asked to look at their structures and identify what they have in common that could tend to lead them to having the same function. And one of the things is that they both have these small structures. They both share that aromatic group. They are similar in size. So for certain functions in our body, so something like a painkiller, these molecules need to fit into pain receptors in order to block signals being received. So they need to be a certain shape and a certain size to be able to do that. And so one of these things these guys have in common, they're small size, they've got those aromatic rings, they're going to lead them to have similar functions. Now, looking at estradiol and testosterone, they are both important hormones. So we're asked what their structures have in common. So one of the things we see is that they have the same ring structure. Even though the estradiol, its 6-carbon ring has the alternating double bonds, they still have the same structure. They've got the 2 6-carbon rings side by side. Then we have another 6-carbon ring and a 5-carbon ring. Those are referred to as a steroidal nucleus. So it gives them similar structures. Now, these are two very different hormones. So they do have some differences that are going to set their properties apart. And one of those differences is the aromatic with the alcohol versus being a ketone. Now, estradiol. The estradiol, diol, 2, all is the alcohol, OH groups, 2 OH groups. Testosterone, ONE, it has that ketone functional group. So we're seeing some of that structure represented in the name, even though these are common names for these compounds. So looking at each of our individual functional groups, we'll start with the alkenes. Alkenes are described as being unsaturated hydrocarbons. So we talked about saturated, meaning it was full. Unsaturated means it's not full. We have carbons bonded to less than the maximum number of atoms, which would be 4. That occurs when we have one or more carbon-carbon double bond. So we've got some examples here. We've got some simple compounds. We've got ethene. We've got propene, 3 carbons, butene with 4 carbons, and 2 butene. So these each have the double bond, making it an alkene. Now we have some more complex structures as well. So we've got pipene. This is what's responsible for, or it's a compound present in pine oil. We've got silonine, which is an oil in celery. And then we've got some oil of ginger. And so all of these structures are containing carbon-carbon double bonds. Some have more than one, some only have one. As long as we have at least one carbon-carbon double bond, it's an alkene. So if we looked at those structures, coming back, we have ethene, propene, butene, pipene, silonine. These all have the ene ending, corresponding to being an alkene. If we look at each of their parent names, so looking at those simple structures, we can look at ethene. The ene meant it had a double bond. The eth meant 2 carbons. So we still see the same parent names being used. We're just changing the ending to indicate an alkene. And if we look at 1-butene versus 2-butene, that indicates where double bond is located. Our next family are the alkynes. They are also unsaturated hydrocarbons. They contain one or more carbon-carbon triple bond. So here we've got ethyne, triple bond, propyne, triple bond, butyne, triple bond, or 2-butyne and 1-butyne. So again, same thing we saw before. What all of these have in common is their ending. They all have that YNE ending. They all have a parent name corresponding to the number of carbons in the chain. And then with the butynes, the 1 and 2 are distinguishing what carbon the double bond starts on. Next, as part of our hydrocarbons, we had our aromatic compounds. These are again unsaturated hydrocarbons because they contain double bonds. We have a 6-carbon ring of alternating double bonds, which we call benzene. Now this results in resonance. You may recall from first semester chemistry with your Lewis structures, when we get resonance structures, it doesn't mean that there are multiple structures. It means that when we go to draw those structures, there's more than one way that we could satisfy our octets by sharing electrons. And so we could draw benzene one of 2 ways. We could draw it with these double bonds or with these double bonds. Again, it doesn't mean there's 2 different structures for benzene. It means that the real structure is an equivalent of the 2 so that the electrons get spread as we would see in figure B. Now we get into our functional groups that have atoms other than carbons and hydrogens. So the first one we have are our alcohols. Alcohols are derivatives of water. So a derivative, we talked about this with our, we haven't talked about derivatives yet. Derivatives are going to be where we have one or more hydrogens replaced with an R group. And when we talk about an R group, that's just some grouping of carbon and hydrogen. So we have some examples of propanol. We have 1,2-ethane diol or ethylene glycol. We have 1,2,3 propane triol. So when we talk about alcohol being a derivative of water, so if we have water, this would be our water structure. A derivative replaces one or more hydrogens. So we would have the same structure with one hydrogen, but we'd have some carbon grouping. So these would be our carbon groupings. So they can vary. It's just something attached to that OH group. So we look at all of our alcohols. For structures with more than one alcohol, we notice something with their names. So this ethane diol, I have 2 alcohol groups. We're seeing di. Propane triol, I have 3 alcohol groups. We're seeing tri. So what we see is that the number of OH, which we call hydroxyl groups, is using prefixes. So di, tri, tetra, and so on for however many OH or hydroxyl groups we have. So we're asked in problem 8 to name an alcohol other than ethanol. So ethanol is grain alcohol or drinking alcohol, but you are likely familiar with many other different types of alcohols. And so one example could be isopropanol, which is known commonly as rubbing alcohol. So you may have this at home. It's a common disinfectant. A lot of times if you're given an alcohol wipe to clean in areas, so say you're getting blood drawn or a shot, that's often going to be isopropanol, rubbing alcohol. We've got ethylene glycol. This is antifreeze. This is another type of alcohol you could encounter on an everyday basis. So alcohols have some very common uses. They may be used commonly as solvents. They're very often used as disinfectants. Again, antifreeze, that ethylene glycol. We find them in cosmetics and resins and so on. And again, having that OH group is going to allow it to be used in these different situations. It's also going to impart particular types of chemical reactions, which you would get into in more detail in an organic chemistry class. Next, we have ethers. Ethers are also derivatives of water. They have both hydrogens replaced by R groups. So we would have our water. Our alcohol has one hydrogen replaced. The ether has both hydrogens replaced with R groups. So again, the R is just any carbon grouping. So here we have the example of a diethyl ether. So I have the oxygen, and then my hydrogens are each replaced with these R groups. Ethers have very common uses in solvents, and at one time they were very common anesthetics. Diethyl ether, which we see here, has a history of being used for surgical anesthetics. It's a very common solvent in laboratories. And when we get into our next chapter, when we talk about forming solutions, we'll see why things like ethers and alcohols can make good solvents. Our next family are amines. Amines are derivatives of ammonia. So ammonia is NH3. This is going to be a compound you're going to be very familiar with this semester. Derivatives, again, means one or more hydrogens are replaced. Amines are going to be weak bases. We'll see this in a later chapter. They have common uses in pharmaceuticals. So we saw that with the acetaminophen, had the amine. They're also in our amino acids, a very important building block for our proteins. Amines often have distinct fishy-like odors, as indicated in your worksheet. Something like methylamine is responsible for the smell of very, very ripe fish. So when something smells fishy, you're smelling a methylamine. We have some examples here. So ammonia would be nitrogen with 3 hydrogens. Methylamine would be a derivative. We have 1 hydrogen replaced. Dimethylamine, we have 2 hydrogens replaced with CH3 groups. Trimethylamine, we have 3 hydrogens. Based on the number of hydrogens replaced, because we can have any number of them, we can have 1, 2, or all 3 hydrogens replaced, we can call this a primary amine if 1 hydrogen is replaced. A secondary amine if 2 are replaced, and a tertiary amine if all 3 are replaced. Next, we have aldehydes and ketones. Both families are going to contain what we call a carbonyl group, which is a C double bond O. The difference is the location. Aldehydes have a terminal carbonyl, so it's at the end of the chain. Ketones have an interior carbonyl, so it's going to be sandwiched in between carbon groups. So we would have, if it's at the end, would be an aldehyde. If it's in between carbons, it's a ketone. They have common uses in things like plastics, solvents, preservatives. They're found naturally in our sugars, so you may have heard of things like aldoses or ketoses in your biology classes. These are natural aldehydes and ketones. So an aldose has an aldehyde group, a ketose has a ketone group. So we have some examples here. So if we look at glucose, so one of our saccharides, it is an aldose. It has this aldehyde group. The C double bond O is at the end. Testosterone, which we saw earlier, has the C double bond O in between carbons, so it's a ketone. Acetone, a very common solvent, would be a C double bond O in between two CH3 groups. Now our next family are called carboxylic acids. They're going to contain a carboxyl group. The carboxyl group is basically the carbonyl attached to a hydroxyl. So it'll always be a C double bond O, OH. These are going to be weak acids. We're going to see these come back up again in our acid-base chapter. They're found in nature in fats. They're in our amino acids. They're in vinegar, and so on. So here we have some examples of acetic acid. So acetic acid is going to be vinegar. So here we have that C double bond OH. We have butanoic acid, C double bond OH, benzoic acid, C double bond OH. And then we have stearic acid. This is a fatty acid. This is a long chain fat. It has a C double bond O at the end. So it has a carboxylic acid. Next we have esters. Esters are going to contain a COOC. So it's kind of like that carboxylic acid, but the hydrogen is replaced by an R group. These are formed by reacting a carboxylic acid with an alcohol. So if you take an organic chemistry class, a very common lab would be to synthesize esters. Esters are found very commonly in pharmaceuticals like aspirin. So here we have our ester group. They can be found in fruity odors. So again, a very common lab is to synthesize esters and then distinguish those odors. So oftentimes when you smell like the smell of a banana or a lemon or an orange or pineapple, any type of that fruity odor, those are going to be the result of esters being present. So an example would be pentyl acetate. It's the smell of an apple. We have that ester group present. And then our final functional group are amides. They contain a CON or a C double bond ON. They are formed by reacting carboxylic acids with an amine. They are very important biologically because they are what make up our proteins. We take an amino acid and react the amine end with the carboxylic acid end. This allows them to link. When we get linked amino acids, we get proteins. They're also found in things like nylon. So we have this example of nylon here where we have this C double bond ON making it an amide. Or we have acetaminophen, C double bond ON making it an amide. So that finishes up our chapter 19. As far as functional groups go, we need to be able to look at structures and identify, be able to like circle or locate the functional groups and determine what family it classifies those groups into. Even though we're finishing up chapter 9, this isn't the end. We're going to see these families come up. We're going to see these functional groups come up. We're going to look at their properties in more detail in our later chapters.